Hello dear students. So today, let us calculate the mass defect. So let us calculate the mass defect for the helium nuclei. So the helium contains the 2 electrons and 2 protons. So that 2 protons are equal to the 2 hydrogen atoms and 2 neutrons. So therefore the mass number of the helium is 4 and the atomic number is 2. So if you calculate the mass of 2 hydrogen atom, that is equal to the 2 protons. So that is the mass of 2 hydrogen atoms is 2.01 AMU and the mass of the 2 neutrons is equal to 2.017 AMU. So if you calculate the theoretical mass of the helium atom, so it is the sum of the masses of the protons and mass of the neutron. So that is equal to 4.031 AMU. So the mass defect can be calculated by using this relation, that is Z into mH plus A minus Z into Mn minus M. So that is the Z is the atomic number. So the mass of the two proton, that is the mass of the helium atom theoretical mass is calculated in the above, that is 4.031 minus, so that is A minus Z atomic mass minus the atomic number into the Mn minus M. So it is calculated and it is obtained as 0.030 AMU. So when the helium atom is formed, helium nuclei is formed from the 2 protons and 2 neutrons. Okay, so there is a decrease in the mass which is equal to, that is 0.030 AMU. So according to the Einstein equation, so the disappearance of this mass will be converted into energy. So that Einstein mass energy relation, so we know that it is given by E is equal to mc square. So let us consider an example. So let us consider this example. So now we have to calculate the energy released if the mass defect of helium is 3.040 into 10 power minus 5 kg. So given that the velocity of light is given by 2.99 into 10 power 8 meters per second. So we know the mass energy relation, so that is E is equal to mc square. So if you calculate the energy, so it is 2.73 into 10 power minus 9, that is 9 kilojoule. So when this much amount of mass disappears, so an equal of that is the energy which is released is 2.73 into 10 power 9 kilojoules of energy will be released. Okay, so similarly, so if you calculate the binding energy, okay, so the binding energy we have to calculate in MeV. So when 1 AMU of mass disappears, we have to calculate the binding energy. So we know the mass energy relation E is equal to mc square. So M is equal to 1 AMU. So that is equal to 1.673 into 10 power minus 27 kg. So E is equal to mc square means, so when you substitute the mass and the C square, so you will get 1.504 into 10 power minus 10 joules. So that is equal to, so the 1 AMU will be equal to 1.602 into 10 power minus 13 joules. So that will be equal to 1 AMU. So therefore 1.60 into 10 power minus 13 joules is equivalent to 1.504 into 10 power minus 10 joules. Okay, so therefore if you calculate the binding energy, okay, so that is 931.5 MeV. Okay, so the binding energy of any nuclide can be calculated, so by multiplying its mass defect with 931.5 MeV. Okay, so that is the binding energy is equal to 931.5 MeV into mass defect. So let us consider an example. So calculate the binding energy in MeV of helium atom if its mass defect is 0.03040 AMU. So we know that the binding energy is equal to 931.5 MeV into the mass defect, that is delta M. So the mass defect in case of the helium atom is given by 0.0304. So when it is multiplied with 931.5 MeV, so we will get the 28.3 MeV. So this is the binding energy of the helium atom. So next let us discuss about the decay law, so which is also called as the law of radioactive disintegration. So according to this decay law, so the number of nuclides decaying per unit time is referred to as the rate of decay. So the rate of decay is found to be proportional to the number of radionuclides present at any given instant. So this is called as the decay law or the law of radioactive disintegration. So let us derive the expression n is equal to n naught e power minus lambda into t. So let us derive the equation n is equal to n naught into e power lambda into t. So if dn is the fraction of the total number of the radioactive atoms or nuclides undergoing decay in a small interval of time dt. So the rate of decay, is given by dn divided by dt. So according to the decay law, so the rate of decay is given by, so that is equal to minus dn divided by dt is proportional to n. Okay, or minus dn divided by dt is equal to lambda into n. So let us call this one as equation number 1. So where lambda is called as the decay constant. So it is the characteristic of the radionuclei and has the unit per time. So the equation 1 is identical with the rate law for the first order reaction. So unlike the rate constant of a chemical reaction, and the lambda is independent of the temperature. So here we have to note that the rate of decay of a radionuclei follows the first order kinetics. So if you rearrange the equation 1, so that is rearrange the equation 1, so you will get minus dn divided by n is equal to lambda into dt. So let us call this one as equation number 2. So integrate the equation 2. So you will get minus ln into n is equal to lambda into t plus c. So call this one as equation number 3. Okay, so where c is called as the integration constant and which may be calculated. So the c is the integration constant. so which may be calculated. So when, for example, when t is equal to 0, n is equal to n naught. So if you substitute these values in equation 3, you will get minus ln naught is equal to lambda into 0 plus c, or c is equal to minus ln n naught. So substitute this in equation 3 again. So you will get minus ln into n is equal to lambda t minus ln into n naught, or ln n naught divided by n is equal to lambda into t. So let us call this one as equation number 4, or this can be written as ln into n divided by n naught is equal to minus lambda into t. So take anti-log, so that is take anti-log, so that is n is equal to n naught e to the power minus lambda t. So by converting equation 4 using log to the base 10, so you will get, that is lambda is equal to 2.303 divided by t into log of n naught divided by n. So you call this one as equation number 5. So where n naught is the radioactive material initially taken and n is the amount of the present at that time.